start is public defense. My name is Ilya Svichkov. I'm an associate professor in this photonics unit in this department. I will chair the session. So today I have public defense by Tomas Kristijonas Uždavinys. He will present his thesis work. This work was done at the photonics unit here at the Department of Applied Physics in Chista, and his supervisor was Professor Acknowledgment. So the opponent of Tomas today will be Professor Audrius Alkauskas, who came all the way from Lithuania. So Professor Alkauskas has a background in semiconductor physics, specifically radiative and non-radiative processes in semiconductors, studying from theory, like density functional theory, but also defects in semiconductors for different applications. So welcome. Today we have three distinguished committee members who will evaluate defendant presentation of his work. So let me introduce them one by one, the way they sit from me. So first is Dr. Bertrand Noharet. He is with Sveria MAP right now. He has strong background in optoelectronics and he used to work at Rise Acreo on different optoelectronics devices and architectures. So next we have Dr. Qingwan. She is now with Rise Acreo and she has also strong background in physics of non-electronic devices, and she worked a lot specifically with these 3-5 semiconductor materials. And the furthest from me is Professor Anders Hallén. He is part-time with Uppsala University, part-time here with KTH, and right now he is the director of Ion Technology Center in Uppsala, and his main research topics are ion beam modification of semiconductors, doping, and defects in semiconductors. He has supervised 13 PhD students, if I'm right. So we have all these distinguished committee members. They will evaluate Tomas' performance today. And before we start, let me just remind you about the procedure. So first, Tomas will present his work, and then we will take a short break to stretch legs. And after that, opponent and Tomas will engage into discussion. So they will be here, and the committee will be listening to their discussion, everybody in the room. And after that, the committee will have a chance to ask Tomas about his work. And only after that, anyone from the audience can raise questions and ask Tomas. Now, the last comment, please make sure that mobile phones are switched off or turned into silent mode, not to disturb. Please.
Thank you for the introduction. So, good morning, everyone. I'm going to present my Ph.D. thesis, Optical Properties of Gallium Nitride and Indium Gallium Nitride, Studied by Time and Spatially Resolved Spectroscopy. This work had two underlying themes, time and spatially resolved spectroscopy. Therefore, my presentation will be grouped into two sections, showcasing 4 research projects. Before presenting the main results, I would like to provide a quick introduction on why is it important to study gallium nitride and indium gallium nitride, how nitride devices impact our lives, what are the main issues when working with this material system, and finally, how does my research contribute in developing the next generation semiconductor devices. Gallium nitride and indium nitride are both direct bandgap semiconductors, which can be used to grow ternary indium gallium nitride alloy. On one hand, InGaN bandgap can be tuned through whole visible wavelength range. On the other hand, due to large constant difference, crystal growth is rather complicated. For this reason, majority of research focused on low to medium indium content layers, which then can be used to fabricate light-emitting diodes, LEDs, solar cells, transistors, or laser diodes. The blue LED is probably the most known nitride device. The inventors of blue LED were awarded a Nobel Prize in 2014 for development of new, energy-efficient, and environmentally friendly light source. One can simply compare color spectra of LED and incandescent light bulb. White LED emission covers only visible range. For the incandescent light bulb, majority of energy is wasted as heat. This results in tenfold increase in energy conversion efficiency when using LEDs. For instance, US Department of Energy calculated that in 2016, 137 terawatt hours were saved due to adoption of LED technology. To put it in perspective, this is more than the largest power plant in the world produces energy every year. Unfortunately, it is still only 23% of that what could be saved if LED technology were to be fully implemented. That being said, the future of LEDs looks bright, as in less than 20 years, LEDs should represent the majority of all lighting sales. For solar cell applications, it is useful to review air mass reference spectrum. Our semiconductors used for solar cell applications cover only half of the spectrum. Here, indium gallium nitride and gallium nitride enables us harvesting the high energy tail of solar emission. At this moment, photovoltaic market is dominated by silicon cells for their ability to manufacture high surface area elements. Pre-5 semiconductors such as phosphides and arsenides offer multi-junction cells for higher price but with much better efficiencies. By incorporating gallium nitride and indium gallium nitride on these multi-junction cells, efficiencies of 70% could be achieved. While these cells most likely will not be for the mass consumer market, the success of space exploration depends on our ability to manufacture highest efficiency solar elements. For electronic applications, gallium nitride has the lowest breakdown voltage versus on-resistance times area. This results in greater efficiencies when using gallium nitride transistors at high output powers. In addition, gallium nitride transistors are used in high-frequency wireless communication, which helps to communicate and safely land planes. Finally, indium gallium nitride laser diode revolutionized the data storage industry. It allowed storing 4 times more data on same size physical disk. In addition, InGaN lasers can be found in car headlights, are used for medical diagnostics, are only present in nightclubs and entertainment industry, are used for laser projectors, just to name a few examples. Now, despite the success of all these devices, not all material properties are agreed on. There are still many growth-related issues that need to be solved. Most notably, InGaN growth experienced a phase separation, which results to different indium incorporation rates at different sites of the sample. This, for increased indium content layers, results in the production and generation of high density of defects, which is detrimental for light emitters in the green gap. In addition, mechanisms of doping, how impurities are incorporated, what energy states are introduced in the bandgap are not yet fully understood. These issues emerge during the device development and optimization phase. Let's take an example, LED. On paper, one needs to grow only 3 layers, P, N, and an active region for additive recombination. While these 3 layers are sufficient to explain the principle of operation, real-life devices are much more complicated. They consist of many more layers responsible for different functions. Now, therefore, during the device development, these layers are usually grown separately and then, using various characterization methods, are analyzed. Photoluminescence among these is one of the most popular. It offers quick and non-destructive way to study not only optical properties, but also electronic structure, carrier cooling dynamics, chemical composition, etc. This is where my PhD project comes into play. The work was done at ultra-fast and near-field spectroscopy laboratory. Here, ultra-fast carrier dynamics could be investigated, and optical properties could be resolved with sub-wavelength spatial resolution. During this work, gallium nitride templates, which are used for electronic device fabrications, were investigated. In addition, potential quantum belts, which could be used for LEDs and laser diodes, were studied. By better understanding the physics and growth-related issues of these layers, device performance improvements could be achieved. This brings us to the first research project, Intervalley carrier scattering and gallium nitride. Energy difference between lowest conduction bands is a fundamental material property which affects the performance of electronic devices. Most notably, it defines electron saturation velocity. By applying electrical field, we start to populate electrons on main conduction band. After the threshold energy is reached, intervalley carrier scattering can be induced. The satellite valley has lower mobility, therefore, with increased electrical field, overall electron velocity is reduced. In case of gallium nitride, this value is still disputed. Reported values could be grouped into two groups, around 1 electron volt and 2 electron volt. Recent photoemission measurements reignited conversation between different groups. Therefore, we decided to revisit this value by conducting an independent measurement. We chose to use pump row spectroscopy, which is a measurement technique used to study ultrafast carrier dynamics. In this measurement, laser pulse is split into two parts. Stronger pump is used to induce non-equilibrium states in the sample, while the weaker one, probe, is used to study pump-induced changes. By changing the travel distance of probe, pulse, optical constants can be measured as a function of time. In this study, two pump probe configurations were used. In differential reflection, intervalley carrier scattering was induced with UV pump, while electron relaxation was monitored with infrared probe. In differential transmission measurement, both pump and probe pulses were in infrared and near infrared range, so that only states in the conduction band could be probed. I will start the results from differential transmission. Studied gallium nitride samples were unintentionally doped. In other words, at the bottom of main conduction band, we had some peak carrier concentration. If our pump beam energy is below that of intervalley energy, one would expect to measure fast electron relaxation. In case pump energy exceeds intervalley energy, due to carrier scattering, transients are expected to slow down. This is indeed what we observed in the experiment. With increased pump energy, decay times slow down. By plotting decay times versus pump energy, threshold-like behavior is observed. Here one should mention that carrier scattering participates with assistance of longitudinal optical phonons. Therefore, we can use a very simple equation by subtracting phonon energy from our measured threshold energy. Intervalley energy is experimentally evaluated. We also wanted to double-check this value, therefore an additional measurement was conducted. In differential reflection measurement, UV pump was used to excite electrons from the valence band. Here again, if the pump energy is below intervalley energy, one should expect to measure fast processes. In case pump energy is able to induce intervalley carrier scattering, then transients are expected to slow down. This is also confirmed with experiment. With increased pump energy, rise time slow down, plotting rise times versus pump energy reveals a second threshold-like behavior. Evaluation of intervalley energy from differential reflection measurements is slightly more complicated. One has to take into account the non-parabolicity of the valence band. Nevertheless, using the available data, a similar value of 1 electron volt is confirmed. Now, differential reflection measurements gave us an opportunity to study electron scattering dynamics. In short, differential reflection signal is inversely proportional to electron mass. In other words, at longer times, signal tells us that all electrons relax at the bottom of conduction band, where the effective mass is the lowest. Then, we can describe our system with discrete energy levels, and then, using system of rate equations, model the experimental data. For transients below intervalley energy, phonon relaxation rates are evaluated. For transients above threshold value, intervalley scattering rates are determined. brings us to the first set of conclusions, first project. Energy difference between lowest conduction band was experimentally determined. In addition, electron longitudinal optical photon scattering rates were evaluated by modeling reflection transients with rate equations. These results were published in the paper A. In research project number 2, photoexcited carrier trapping in iron-doped gallium nitride was investigated. Gallium nitride is often contaminated with silicon and oxygen, which acts as shallow donors and results in peak carrier concentrations at room temperature. Brewing devices directly on unintentionally doped gallium nitride, for instance, high electron mobility transistor, would result to leakage currents, which reduces performance and leads to premature device degradation. One of the methods to solve this is intentionally doped gallium nitride with iron, which introduces deep acceptor states and allows us fabricating semi-insulating layers. On the other hand, iron could be introduced unintentionally. Having deep states in the band gap might lead to efficient non-radiative recombination rates, which would be detrimental for optoelectronic device performance. For this reason, in order to evaluate both positive and negative aspects of doping with iron, carrier trapping dynamics should be understood. In this study, streak camera was used, which allows resolving combination in gallium nitride. One would expect that doping with iron, deep states are introduced in the band gap, which should affect the combination properties, photoluminescence transients. First, one should check the reference sample, which wasn't intentionally doped with iron. We observed typical double exponential transients with a longer component of few hundreds of picoseconds. Photoluminescence transients are drastically affected even with smallest iron concentration. Samples with lowest iron dose leads to single exponential decays with decay times of few tenths of picoseconds. By plotting decay times versus iron concentration, a linear dependence is observed. We know that in our studied samples, the dominant impurity is iron, and in current experimental conditions, iron is predominantly in its 3+ state, which acts as an efficient electron trap. Therefore, we can attribute the drastic changes in photoluminescence to electron trapping and evaluate electron capture coefficient. Before presenting Hall capture coefficient, I would like to review processes during our experiment in slightly more detail. As mentioned before, prior to photoexcitation, iron is predominantly in its 3+ state. After exciting samples with a laser, we generate electron-hole pairs. Electrons can then be trapped by iron 3+, which via charge transfer transforms into 2+ state, which can then act as a hole trap, and via reverse charge transfer process return back into 3+ state. We conducted excitation-dependent measurements. In other words, excitation is proportional to electron-hole pair density. For low excitation densities, when electron-hole pair density is much lower than molar than iron concentration, we see excitation-independent lifetimes, which can be attributed to electron trapping through iron 3+ state. Under highest excitation conditions, when electron-hole pair concentration exceeds that of iron, initially after the laser pulse, iron 3+ state captures electrons, and the dominant capture process becomes iron +2. Thus, we see this double slope exponential shape emerging. This allows us to describe the system using system of rate equations. We already evaluate electron capture coefficient. Then, having single unknown value, we can determine Hall capture coefficient. After determining these coefficients, two problems emerge. First of all, our electron capture coefficient is much larger than reported by other groups using different experimental setups. Second, iron 2+ state is known to be close to valence band, is the conduction band, while iron 3+ state is close to the mid band. Capture coefficient is exponentially proportional to the distance to the defect level. Thus, having a high Hall capture coefficient contradicts commonly known knowledge. For this reason, we decided to look in more detail into ions inside gallium nitride. Both +3 and +2 states can have either ground or excited states. By redrawing our model, by including these states into our model, having the ground states and excited states, we see that internal relaxation from excited state into ground state is in the millisecond to microsecond range. In our experiment, time between ultrafast laser pulses is only 30 nanoseconds. In other words, there is not enough time for excited states to relax to the ground states. Thus, our evaluated capture coefficient should be attributed to the excited states instead. And it's well known that excited states have much larger capture coefficients than their ground states. Therefore, the second project's main conclusions were the discrepancies between electron capture coefficient and measured high Hall capture coefficient can be solved by considering excited states. In addition, electron and Hall capture coefficient were determined. Two takeaway things from this study are that when conducting numerical modeling of devices who have iron-doped layers, one should use the appropriate electron capture coefficient. For devices intended for low current densities, capture coefficient to the ground state should be used. For devices aimed for ultra-fast optoelectronic applications, capture coefficient to the excited state should be used instead. Second, if iron is introduced unintentionally, under typical LED currents, iron ions would be predominantly in their excited state, hence acting as efficient non-radiative recombination centers. Thus, for optoelectronic device applications, unintentional iron doping should be avoided at all costs. The results were summarized and published in paper B. This brings us to the second part of my presentation, spatially resolved optical properties, and I will begin from indium gallium nitride epitaxial films. For lasers to have high modal gain and low lasing threshold, spontaneous emission needs to be spectrally narrow and spatially uniform. In case of gallium nitride, there are three mechanisms responsible for photoluminescence broadening. In order to study only one of those mechanisms, we investigated indium gallium nitride epitaxial films. Having epilayers instead of quantum wells allows excluding quantum bell width fluctuations. Growing layers between the critical thickness, in other words, having them stressed, allows not having stress relaxation induced processes. Thus, we can study how photoluminescence broadening is directly affected by composition variations. One should mention that photoluminescence provides information only about the extended states introduced due to broadening. Absorption measurements is more correct way to study all extended states. For this reason, our colleagues at EPFL drew a large set of indium gallium nitride epitaxial films with different indium compositions and measured absorption line widths at low temperature. Then they applied conventional random alloy model and found that only at very low indium content layers, line widths can be described by a model. For increased indium molar fraction, line widths progressively deviate from this model, from predicted values. Therefore, samples were investigated here at PTH using scanning near-field optical microscope, SNOM. We used second harmonic, which with the help of a long-pass optical filter was coupled into the fiber. At the other end of the fiber, we have a metal-coated probe. Here is a typical, this is a SEM image of a typical scanning near of one of the metal-coated SNOM probes. One can observe sub-wavelength aperture. Then, This probe is positioned in close proximity to the sample, where near-field excitation can be generated. Using a feedback loop, the probe to sample distance is controlled, which allows us measuring the morphology. Optical signal is then collected back through the probe aperture and analyzed outside using time-related single photon counter and spectrometer, which then allows measuring different optical properties, and then, for example, taking photoluminescent peak wavelength, spatially mapped. This is a large-scale 50 by 50 micrometer FM scan of one of the studied samples. Depending on growth condition, different morphologies can be formed. The studied samples were grown under step flow conditions, thus we see this large-scale surface undulations. We then scan different areas of the sample with a scanning near-field optical microscopy. We took the peak energy position of our near-field spectra and converted it into indium content. By superposing our indium content maps, we see that there are large indium composition fluctuations, which visually seems to correlate with these undulations. Therefore, we decided to do a more detailed SNOM scans. Here is an example 10 by 10 micrometer. By calculating morphology gradient towards x direction, we observe that the direction of the slope strongly correlates with both integrated intensity and peak energy. We can then take example spectra and observe that there are red-shifted indium-rich slopes which emit stronger emission, and there are blue-shifted indium-poor slopes which emit weaker emission. To understand the origin of different indium incorporation on different slopes, we decided to look at the template on which the epilayers were grown. This is an FM scan or large scan of gallium nitride template. One can see this monolayer step edges form. If we would zoom in on this map, we can identify different crystallographic orientations and notice that there are two different slopes. One slope is aligned with crystallographic orientation, and the terrace width, or distance between step edges, is narrower, while another slope, due to surface mistake, deviates from a crystallographic orientation, and the terrace width is larger. Now, incorporation of metal ions strongly depends on the available nitrogen bonds. In other words, indium prefers to be incorporated when there is a single nitrogen bond available, while gallium prefers to incorporate it where there is double bonds available. Now, different crystallographic planes would have different number of available nitrogen bonds. They're usually called type A for double bonds and type B for single bonds. Using this schematic illustration, we see that if metal ions land on slope 1, they can be incorporated only at type B edges, hence indium incorporation is preferred, indium-rich slope is formed. For the slope 2, where we see this deviation from crystallographic orientation due to zigzag structure, metal atoms can be incorporated both on A and type B slopes, hence indium-poor slope is formed. Therefore, the main conclusions of a third project are that random alloy model can only be applied to low indium content samples. For increased indium molar fractions, line widths progressively deviate due to long-range fluctuations induced by step meandering. Finally, it was demonstrated that indium composition strongly depends on geometry of step edges formed during growth. Results were published in papers C and D. In the last research project, indium gallium nitride single quantum wells were investigated. Quantum wells are the building blocks of both LEDs and laser diodes. Usually, they are grown as sets of multiple quantum wells to have larger active volume. Nitride technology is primarily based on pole and C plane, which, due to internal piezoelectric field results in formation of triangular-like quantum bells. One can observe the overlap between wave functions is reduced, hence radiative lifetimes are prolonged. In order to combat this, quantum bells could be grown on non-polar, M-plane, or semi-polar planes, thus increasing the overlap between wave functions. Before growing a complicated device with multiple quantum bells, it is useful to investigate for a single quantum bell. One of the two most important parameters are radiative and non-radiative lifetimes, as these define the internal quantum efficiency of a structure. These values are usually evaluated using conventional far-field spectroscopy technique. The laser beam is focused on the sample, and then photoluminescence transients are measured at low temperatures. For samples with low defects, at low temperatures, one can assume that within first picoseconds, recombination is purely radial. Then, for such samples, with increased temperatures, radiative lifetime would be inversely proportional to transient amplitude. By measuring transients at room temperature and using this conventional equation, radiative and non-radiative and radiative lifetimes are evaluated which are averaged over the size of our laser beam. Now, snow measurements on one hand offer a much better resolution. On the other hand, at least with our equipment, these measurements can only be done at room temperature. Therefore, in addition, we can resolve photoluminescence transients with 100 nanometers spatial resolution. Then, by calculating local amplitudes and local lifetimes, we use an assumption that variations for our low defect samples, variations in amplitude in our studied samples, is due to variations of internal quantum efficiency. Then, by using our spatially averaged radiative lifetime under the measured in the far field and local variations of amplitude, local radiative lifetimes can be evaluated. Knowing radiative lifetimes and photoluminescence lifetimes allows us to spatially map non-radiative lifetimes. This is an example of one of the studied samples, white M-plane. One can observe two things. First, both types of lifetimes are not spatially uniform. Second, one can observe areas with prolonged lifetimes, which seems to correlate with surface morphology. M-plane quantum bells are known to be M-plane quantum bell surfaces are known to be contaminated with this pyramid-like hillocks. This is a high-resolution FMRAP, and this M-plane is non-polar, but when these defects, pyramid-like hillocks, are introduced, different faces facing different polar crystallographic orientations are formed. Then, to understand the origin of prolonged times, it is useful to invoke the notion of carrier localization. In nitrides, holes are known to be strongly localized, well-defined in space, while electrons are not. In case of flat quantum, these pyramid-like hillocks are formed because the surface charge accumulates next to the interface, and small electric field is introduced into our quantum bell structure. Thus, an in-plane component is introduced, which can then push our weakly localized electrons in space, hence reducing the overlap between spatial overlap between electrons and holes, prolonging the radiative life. Finally, I would like to return back to photoluminescence in case of single quantum bells. Because this is a more complicated structure, we can no longer avoid quantum bell width variations, which does affect the transition energy. In addition, composition variations would also lead to variations in transition energies. Therefore, when people are studying quantum bells, photoluminescence broadening is usually attributed to these two processes. We again decided to try to differentiate them by conducting a simple experiment. First, we modeled transition energy variations by few monolayer fluctuations. Then, samples were grown at University of California, Santa Barbara with same indium content but different quantum bell width Finally, samples were measured here at KTH using scanning near-field optical microscopy. These are the full-width half-maximum snow maps. One can observe from color bars that full-width line width variation increases with quantum well thickness. By plotting the average line width versus quantum well width, we observe a positive trend. Now, our simulations show that biggest quantum well width thickness variations would have largest effect for the narrowest quantum well. In other words, one would expect, if quantum well width variations would be the dominant mechanisms, one would expect largest line width for the narrowest quantum well. Thus, photoluminescence broadening in these structures are mostly determined by composition variations. In the last set of conclusions, it was shown that common assumption of spatially uniform radiative lifetimes is not correct. In addition, the non-planarity of quantum well interface can strongly affect radiative lifetimes. And finally, for moderate to high indium content quantum wells, photoluminescence broadening is primarily defined by composition variations. Results were published in papers E and F. To conclude, this work would never happen without samples provided by Kima Technology, Jim Speck Group at University of California, Santa Barbara, Nicolas Grandjean Group at EPFL. The work at KTH was conducted by 4-people group, which pictures I put in this slide. And to have, last slide, I was looking at this presentation, and one might say that I was exposed to many experimental techniques, but this is the layout of the lab in which experimental work was done. But when you put into scale the size of me, I would argue that a lot of experimental equipment was exposed to me. At least at this moment, majority of equipment is still in the operational mode, which I consider the biggest success of this PhD project.